determinants, we've discussed it. We haven't really talked about what a determinant is. In fact, you see a lot of notation here that talks about how to come up with the determinant without ever really talking about what it is. A determinant's actually very easy. In 2 dimensions, it's very easy. It's just an area. But I'll get more specific on that in a few minutes. So the definition of a determinant, if you think about it as a number that represents the value of a matrix, that's probably not the worst way to think about it. It's just a question of what the value would be. And so if you know that it's an area, then in 2 dimensions anyway, then that kind of gets you going in the right direction. But of course, the follow-up to that would be the area of what? You know, and then what if it's in 3 dimensions? Are we still talking area? No, then we'd be talking about volume. And in 4 dimensions, what did he even call that? You know, so yeah, there's more to it than that. But I can start you off with something very simple, and I'll just kind of chuck it off on the side here. It's if I wanted to find, you know, just starting off with, because it really doesn't require much. If I were to start off with, it's our basis vectors, I and j. All right, so, and create a parallelogram. In this case, it would be a rectangle, using the sides of I and j. Okay, so just the way we would if we were to find the sum of I and j. If I were to say, what is I plus j? Graphically, what would you do? You would reproduce j over here, I up here, and then draw the diagonal. That would be I plus j. Okay, that's not what I'm asking for here. We're looking for a determinant. A determinant would be the area of this rectangle. Because really, what are we talking about in geometry? We talk about, most often in 2 dimensions, we talk about lengths and areas. Okay? So we talked about lengths a lot, sums, differences, things like that. Even a dot product, you're still getting into lengths. Now we're getting into areas. So really, it's just a different geometric component. Right? So if I wanted to find the determinant of ij, so that would be, I'll just call it matrix A, is the identity matrix 1, 0, 0, 1. The 1, 0 is the I. And the 0, 1 is the j. The determinant of A, we were doing diagonal down minus diagonal, AD minus BC. But if we just look at it, it's like, what is the length of this side? 1. What is the length of that side? 1. 1 times 1, 1. Okay, it's the area contained within that rectangle. Right? Now, I said parallelogram because it really is parallelogram, because we can't always guarantee that the 2 vectors that we're dealing with are going to be perpendicularly intersecting. So if I had something, just a quick sketch, something like this, 2 vectors in space, then I would have to create the parallelogram as if I were trying to find the sum of those 2 vectors. The area contained would be the determinant. All right. So here we're going from I to j in terms of vector 1 in the matrix is I, vector 2 is j. It's a counterclockwise movement. In 2 dimensions, very easy to see, because you think about the unit circle, for example. Counterclockwise is a positive movement, clockwise is a negative movement. Right? It's the same idea for determinant. If you're dealing with a counterclockwise movement, your determinant should be positive. If it's a clockwise movement, your determinant should be negative. Right? So, and you can verify that pretty easily. Very easily. If I wanted to find the determinant going from j to I would reverse the columns of the matrix. If I did my AD minus BC at that point, I would get a negative 1. All right, so positive or negative values, just they're discussing the orientation or the movement from one vector to the other, but it's only the absolute values that we care about. Because if we're talking about area, we're talking about the absolute area. All right, so if I were going from the vector closest to the x-axis here to the one closest to the y-axis, I would expect a positive determinant. But if I were going the other way, I'd expect a negative determinant. But it is the area that's captured within that parallelogram that is known as the determinant. Right? And it's kind of like standard deviation in statistics. It's a comparative measure. Determinant of one compared to the determinant of another. You know, it gives you a sense of size. Also, you kind of learn a little something about, you know, under what circumstances would a determinant be equal to 0, for example. Well, it would have to contain no area, right? So it would make sense that if two vectors were pointing off in the same direction, they would not contain any area, in which case your determinant would be equal to 0. And so that's a little bit of a geometric representation of determinant, but we're going to actually get into the discussion of how you can compute these things. And the permutation concept, it's kind of, I don't know, it's a little out there. I'm not going to ask you to do this on a test. I mean, unless you start like laughing at my jokes or something. I get like one chuckle out of that thing. And a sneeze. A derisive sneeze. Thanks a lot. Bless you, by the way. The permutations we know are arrangements. You know, that's from like high school, middle school. Right? So if you have 3 people and you want to arrange them in a line containing all 3 folks, how many ways could that happen? Any of the 3 people could be in the first position, then any of the 2 remaining people in the second position, and so on. You know, if you have 30 people, it's a bigger set of possible arrangements. If you only have 2 people, then there's only 2 possible arrangements. Right? So it all depends on the size of the sample set. Right? So in our situation, what that means is it depends on the size of the matrix. Because if you're dealing with a 2x2 matrix, nice and easy. Only 2 possible ways to arrange things. But if you're dealing with a 10x10 matrix, you have 10 factorial ways of arranging things. Right? So that would suck. I used to know that. I used to know 10 factorial. I want to say 3628800, but that can't possibly be right. That's not so. It is right. Right. So, okay, cool. So we've accounted for 3 things in this course. 1, you don't like my videos. 2, you don't laugh at my jokes. 3, when I know 10 factorial off the top of my head, you are not even remotely impressed. I'm not going to say it's like the worst class ever, but like on my Mount Rushmore of worst class ever. Like, no, I'm just kidding. I don't know if I'm kidding. I thought that was something. Anyway, so an example I indicated, 1, 2, 3, if I rearrange the 3 individuals, there's 6 ways that could happen. 3 to occupy the first position, 3 ways, then any of the 2 remaining individuals to the second position, and then all the leftovers. All right, we do this in statistics in the form of a tree diagram, at least to get started, because it's a little easier to see. Where we would say you'd have 1, person 2, person 3. After person 1, it could be person 2 or person 3. After person 2, it could be person 1 or person 3. After person 3, it could be person 1 or person 2. If I have person 1 and person 2, it's person 3 left over, then person 2, 3, 1, 2, 1. Right, so that's our 6 permutations. You know, factorial, it falls under the umbrella of a permutation. So if I say 3 factorial or 3p3, it means the same thing. Because really all a permutation is limiting what a factorial is. So if you wanted to know one thing, you'd learn the permutation because it encompasses the concept of a factorial. Right. So follow each branch to its endpoint, you know, like partial derivatives 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, and so on. But among the process of finding permutations, we stop just caring about the order itself and start caring about being in the right order, right? Forwards and backwards, right? Because we have a set here that's preordained to be in the order of 1, then 2, then 3, right? So we talk about what are known as inversions of the orders, right? If you invert the order, that's going to negate the order. So forwards is positive, negative is backwards. It's the same way in physics, it's the same way in calculus. You know, so why would it be any different in linear algebra or probability and statistics? You know, so it implies direction. Right? Sometimes it means other things, but generally speaking, I mean, you talk about like a standard deviation, you know, like it's a square root of a number. So you're talking about technically it could be positive or negative. But are you really looking at a negative number in that context? Probably not, because you're just looking at a measure that represents the spread of the data, right? So there are exceptions to everything, but in most cases it implies the order of the data or the information. All right. So if I have the information in the order that it was originally presented, we say that there is no inversion. It's in the correct order. If it's in any other order, there is some kind of inversion. It's just a question of what type of inversion. All right. So how do I get from 1, 2, 3 to 2, 1, 3, for example? Well, I can swap the 1 and the 2. That would be a single inversion, right? To get from 1, 2, 3 to 2, 1, 3, all I have to do is make one switch of consecutive numbers. We're only talking about consecutive numbers. So if I wanted to change the 1 or swap with the 1 with the 3, so make it 3, 2, 1. That would actually be 2 conversions, because if I'm only allowed to swap consecutive values, then I couldn't get it done with one inversion, right? So that's one of the definitions of the term inversion, right? So to get to 3, 1, 2, somehow the 3 has to get to the front. Well, I can do that by working off of something that I've already done. You know, just kind of look at one of the other inversions and go from there. Or I can just kind of take it from scratch and say, right, I want the 3 to go to the front and the 2 to go to the back. So if I swap the 3 with the 2, the 3 would be in the middle, and then swap the 1 with the new 3 in the middle, it would become a 3, 1, 2. That would be 2 inversions. I need 2 movements in order for that to happen, right? So you just start thinking about it. Is using only movements of consecutive values? How can I get from the original ordering to my new ordering? Personally, I found it helpful when I was first kind of investigating this to specifically with just 3 numbers. Take the number 1, write it on an index card, take the number 2, write it on another one, and take the number 3, write it on another one. And just say, okay, I want to get to 3, 2, 1 by only swapping consecutive cards. So it's like 3-card Monty, you know? So I'm swapping, and then I'm swapping. Okay, I had to make 2 movements in order for that to happen. Okay, so that would be 2 inversions. Right? The reason why this is important is because it's going to define why, if you know anything about the cross product, you know, we use a concept associated with a determinant in order to find the cross product, but it was always like, all right, the I component had a positive, the J component for some reason had a negative, and then the K component was back to positive. It had alternating signs. It was like, well, why is this? I promised my Cal 3 students that the explanation would come in linear algebra, so here it is. But it has to do with this inversion concept, because we define positive inversions as, positive inversions, odd number of inversions as negative inversions, and even number of inversions as positive, right? Because what happens is you're changing your orientation, yeah, but you're changing it, and you kind of think of it as you're moving forwards and then you're moving backwards, or you're moving backwards and then you're moving forwards. If you make 2 movements, generally speaking, if you're changing your orientation twice, you're facing the direction you started in, right? So it's the old, like, the sports analogy, where you have the professional athlete who says, listen, I know we've been having a hard time. We lost a lot of games, but we're working hard, and pretty soon we're going to make a 360 and get moving in the right direction. It's like, okay, well, that's I think you meant a 180. You know, like change. You're going the wrong way. You want to go the right way. If you do a 360, you're just going to go back in the same direction. So, yeah. So instead of going one full turn, how about 2 half turns, or just stop when you make the 1 half turn? So that's the idea here. If you do 2 inversions, you're changing your direction. You're starting in the positive direction. Make an inversion, you're going negative. Make another inversion, you're going back to positive. Okay? So that's the rationale behind that. And so basically all of this really just kind of illustrates that concept just in a textbooky sort of way. All right. So let me. Oh, I did do it. Okay. I stole my own thunder. I was going to prove it by hand anyway. All right. Anyway. Let me snag this so I can point to it. Where did I write it? Just want to be able to point to it. Make it super tiny. All right, so this is the textbook definition of a determinant. So when you see this, you start enjoying the fact that there are shortcuts to this stuff. The plus or minus a sub 1, j sub 1, a sub 2, j sub 2, and so on. That's the weirdness. But basically, we're talking about different permutations of the j. The j represents the columns that make up your matrix, right? So if I were to, I think my typed or my attempt to type a proof here might actually work against me. So let me do it. Yeah, let me do it out like this. All right, so it's going to essentially end up taking the same form, but you'll see the structure of it a little bit more. So you have row 1, column 1, row 2, column 2. What we want to do is find J, they call it J, which is the number of permutations or the types of permutations of the columns that make up your matrix. All right, so J equals the matrix for some reason. All right, so we have 2 columns, column 1 and column 2. So the possibilities would be 1 and 2, or 2 and 1. All right, so this has no inversions. This has 1 inversion. This would be a positive product. This would be a negative product. All right, even number of inversions, positive, 0 is considered even. Fun fact for the day. 1 odd number would be a negative product. All right. So what we want to do is, working row by row, account for each different type of inversion. All right. So I want to do, so I mean, if I can just fill in the gaps here, it'd be 1, 1, 1, 2. This is what we had before. 2, 1, 2, 2. All right, so really all of this, I think maybe, I don't know, slightly better. I don't know. This felt ugly to me just now. That feels better. You may think it's the other way around. Anyway, so we're going to work row by row. So starting with row 1 and row 2, we're going to count for each of these possibilities. So again, these are the permutations of the column. So column 1, column 2. And we're going to take those results and multiply them together. The resulting product is going to be positive. And we're going to do the same thing for the other possible permutation. Going row by row, A1, A2. Because it's a negative inversion, we're expecting a negative product. And our permutation has us going for the columns of J, 2, then 1. All right, so if we take our matrix that we defined in general terms, A11, A12, and so on, and called it just A, B, C, D. What we'd be looking at here would be the entry contained within A11, which is A, times the entry contained within A22, which is D, as a positive product, minus the entry contained within A12, which is B, times the entry contained within 2,1, which is C. Okay, so AD minus, because it's a negative product because of the 1 inversion, BC. Okay. Now, expand that up to 3 dimensions, and you have a lot of work ahead of you. You know what I'm saying? Because you have a 2 by 2 matrix that's 2 possible permutations. 3 by 3 matrix, you can see the progression. I mean, I have it all here, so it's very enjoyable. But you have to know the number of terms within the matrix so you know what you're aiming for. Then actually develop the number of arrangements within each matrix, within each permutation, I mean. Then count up the number of inversions that it takes to get from 1, 2, 3, for example, to 1, 3, 2, and then 3, 1, 2. Okay, that's manageable, not fun, manageable. Scale it up to a 4 by 4, 5 by 5, 6 by 6. 6 factorial, I think, is 720. So this list would contain 720 items in it. I mean, that's just awful. Right, so definitely shortcuts required. So what we do is I'm going to put shortcuts. We have something called Cofactor Expansion, expansion by minors, and diagonalization. Well, diagonalization looks like, but we can use triangular form matrices to come up with determinants also. All right, so we got this bad boy here, which, I mean, it just looks so dreadful. I mean, look at that formula, it's a beast. The sum from j equals 1 to n, but I just got through telling you that j is just columns. So 1 to n, all right, so 2 by 2 matrix, j would just be 1 and 2. 10 by 10, it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that would suck. All right. -1 to the 1 plus j. All right, so that's an alternating sequence, right? So, I mean, a smidge of calc to it there, but, you know, we're doing a summation, so that makes it a series, but, you know, an alternating series, okay, that means it's going to be positive to negative, or vice versa, right? So that, I'm not intimidated by that anymore. The 1j, right? So what that's telling me is I have a constant 1 for I. So I'm living in row 1, but I'm varying my j from 1 to whatever the maximum number is, right? So if I'm in a 4 by 4 matrix and I have j values of 1, 2, 3, 4, so I'm going to start off with row 1, column 1, then row 2, column 2, then row 2, column 3, row 1, column 1, row 1, column 2, row 1, column 3, and row 1, column 4. And then the last part, that's a little weird. Determinant of A1J, A sub 1J, right? That part takes a little bit getting used to, but really, I'm not going to ask you to plug anything into a formula, but it's actually a whole lot easier than you might think. All right, so let's actually dive into the process here. So first off, it's a 3 by 3 matrix. So we're talking j equals 1 to 3. All right, so not really much there. All I did was rewrite the formula with a 3 on top, so I'm not really doing anything. All right, but I want to organize it in such a way that I can manipulate it and show you what the result is. You'll only be on the hook for what the result is. Okay, so if I start off with a 1 for j, you're going to just kind of play it out. The j value equal to 1. You would have, and we'll just focus on the entry, because we're going to sum all this up later on. -1 to the 1 plus 1 power, a sub 1, 1, determinant a sub 1, 1. All right, so what that means, what that interprets as, the weird component is the capital A sub 1j. The matrix that we're defining this matrix of results if you cross off row 1 and column j and find the determinant of the resulting matrix. Now, if you're working with a 3 by 3, the resulting matrix is going to be 2 by 2. Not bad. If you're working with a 6 by 6, your resulting matrix is not going to be 2 by 2. So, not good. All right. So, it'll always be -1 in each dimension. But what that's telling me is we have a 1 in my first row, first column. The result of -1 to the second power is just a +1. A sub 1, 1 is the entry 1. The determinant that I'm looking for is what would be left over if I crossed off these guys. All right, so we're reducing the dimensions of the matrix that we need to find the determinant of in order to make our lives easier. So I'm finding the determinant. So if you represent a matrix within absolute value brackets, it's indicating that you're looking for the determinant. It's asking for that. So then when j is equal to 2, I'm crossing off the row 1 and the column that it's in and finding the determinant of everything else. Okay, so I have, and I'll write the expression out at least for this one problem, -1 to the 1 plus 2. So that's going to give me a negative quantity, -1. A sub 1, 2, which is a 5. And then the determinant, A sub 1, 2, which is all the remaining entries that weren't crossed off. 0, -1, 1, 0. And so then we only have one more thing to account for, because we're working across the top row. J equals 3, column 3. So -1 to the 1 plus 3, A sub 1, 3, determinant of capital A sub 1, 3. So -1 to the 4th power is a positive 1. A sub 1, 3 is a -4. The determinant of all the remaining stuff, 0, 1, 1, 2. And find the sum. All right, so little calculation required. I need to find the determinant of these 2 by 2 matrices, but they're 2 by 2. That's not going to be difficult. That doesn't mean I'm not going to immediately screw it up, but it shouldn't be difficult. 1 times 1 is 1. Diagonal down is 0. Diagonal up is -2. -2 is 2. -5 times 1 -4 times -1. Well, that's pretty anticlimactic. I'm just checking to see if I screwed anything up. Where's the 2? Oh, gotcha. I was going to say, because this parallel pipe head should have some volume. Yeah, because this 3 by 3 matrix is so 3 vectors off in 3 dimensions. Just like in 2 dimensions, the 2 vectors would contain some area. That area would be known as your determinant in 2 dimensions. In 3 dimensions, it would contain some volume, also the determinant. So that's the geometric representation of determinant in free space. So the only way that that's going to play out to a determinant of 0 is if you're talking about vectors that are multiples of one another. Right? So basically containing no volume. Right? So all you need are 2 vectors, one that is the multiple of the other in order for that to happen, because then they would span the same plane and not create a volume. They would create only an area. But You know, you could have an area but not a volume. That's a possibility.
So if we wanted to like do this on a test, show our work, would we have to do like the -1 to the 1 plus 1, all that, or could we just write out like the...
I need coefficient,
Okay,
determinant matrix coefficient.
Alright, I was wondering if you had...
Yeah, I don't need all the tiny details, but I need some.
Okay.
Alright, so let's see here. Oh, and this is just all this stuff down here. Cofactor expansion allows you to do it across any row or any column. So if you wanted to do it down, for example, the jth column, this would be your expression a sub 1j, c sub 1j, where c represents your cofactor expansion, which is basically what you have up there, it just in a slightly different form. Right? So I think that might be where we're going to leave it off. So let's just do this last one, and then we'll call it a day. I'll get you the quiz, and then we'll be done. All right. So the cofactor expansion across the third row to compute J. All right. So that would be this idea here, but this relationship. All right. So the cofactor itself, -1 to the I plus j, times the determinant based on that ij. All right, so let's start with that component of it. This part here is really just elaborating on the idea that you do have to multiply by whatever the entry is in that row or column. All right, so what we did above was limiting us just to the first row. This is saying that we're not just limited to the first row. All right, so we're doing the third row. All right, so we're assuming I equals 3. So it's a constant I equals 3. All right. So therefore, we would have C of 3j is equal to -1 to the 3 plus j times the determinant of a sub 3j. All right, so we're living in row 3, and that's where we're going to work. All right, so it's still 3 by 3, so we have to allow for j to be equal to 1, 2, 3. All right, so if it's 1, well, we're in row 1, column 1, so my entry here would be 1 multiplied, 1 because that's what the entry is, multiplied by -1 to the 3 plus, we're in j, which is equal to 1, determinant a sub 3, 1. All right, so that's telling me that I need these guys. So we clean it up. It's a +1 coefficient. All that remains is the determinant, whatever the determinant is, of 5, -4, 1, -1. All right, we'll get that in a minute. Then we go to J2. J equals 2, I mean. Value is 2. -1 to the 3 plus 2, determinant of not D, but A, three, 2. All right, so the -1 to an odd power is going to be negative, so we're looking at coefficient of -2. The remaining entries, if we disregard only the elements in this column, would be 1, -4, 0, -1. And the last one, coefficient of 0 multiplied by meh. It's going to be 0, right? No matter what it is. So 5 minus -4, so 5 plus 4. Oh, sorry, -5. Minus 2 times, we got 1 minus -4, so 1 plus 4 plus 0. I did it again.
The 4 was right.
Diagonal up should be 0, right?
Oh, yeah.
I thought that's what you were talking about. I didn't even catch the negative. So I'll just write -0. It doesn't really matter. But. So -1 plus 2. So 1. So clearly, all the answers to any 3x3 matrices, they're all going to be equal to 1. So you don't have to show any work. Just put 1 as your final answer for every question, and you'll be fine. It's not true, in case anybody